there's a non-zero thing to the left of it. So this column, which represented z, does not have a leading 1, so that must mean that z is an arbitrary parameter. So z is arbitrary in this example here. Okay. So z is our arbitrary parameter. Great. What does that mean? Why do we call it arbitrary parameter? Well, basically what it means is that z can take any value that I want. If I pick any number for z, I will get a solution. So for every choice of value for z, you get a solution to this system of equations. This is why there's infinitely many solutions, because there are infinitely many numbers for me to choose from for z, and each one gives me a solution. So if I pick z equals 17, I get a solution. If I pick z equals -3, I get another solution. What do those solutions look like? Well, let's use these equations and find out. I know that x minus z equals 7 and y equals 3. And I can kind of ignore the 0 equals 0 because that doesn't tell me anything I don't already know. So what I'm going to do is solve this first equation so that I get x, which is not arbitrary, in terms of z, which is arbitrary. So I'm just going to solve for z, or for x, I should say. And here is my new system of equations that I'll get. I'll get x. I'm just going to add a z to both sides up here. So z plus 7, and then still y was equal to 3. Okay. So this right here, where I've sort of got the arbitrary parameter to the other side of the equation, this represents all solutions to my original system of equations. So I'll write here, each choice of z gives a solution. If you know anything about functions, if I were to use that terminology, which maybe you do or don't, we could say that x is a function of z, meaning that anytime I pick a value of z, it determines a value of x. That's what this represents here. So again, if, maybe I'll write this up in the corner here. So here are some examples of solutions. If z equals 0, then my solution is, I plug in z equals 0, well, that's just going to make x equals 7, y equals 3, and z was 0 is what I chose. So there's one solution. If you go back to the original system of equations and check, this should be a solution. Here's another solution. I don't know, z equals negative, 4. Z equals -4. If I plug in z is -4, that's -4 plus 7, that's 3. So x has to be 3. Y is still 3, and then z I said was -4, and so forth. I can just keep choosing different values for z, and it'll tell me what x has to be. And then y is always 3 because I have this equation. So every choice of z determines the solution. So I have infinitely many solutions. Okay. And then the last thing I'll tell you is that this over here that I had, this x equals z plus 7 and y equals 3, is an example of what maybe in this class I will call a solution in general form. Solution in general form. So I think maybe this terminology shows up on the activity. All I mean is give me the equations where you've moved all the arbitrary parameters to the right side of the equation. That's really all it means, is get everything that's not arbitrary in terms of the arbitrary stuff. So solving it out like this is what I mean by general form. Okay, so we'll pause here. Does anyone have any questions? Again, maybe I kind of dump a lot on you here. You guys have any questions?
I do have a question, actually.
Yes.
So back to like the it's like x minus negative y minus z equals 1, and then like the third one was like at negative x plus 2y plus z. Couldn't you have just switched, like put those, like, I don't know how to explain this, but couldn't you have just, instead of putting the 2x minus 3y minus 2z in the middle, can you just like switch them up?
So you wanted to switch the order of the rows, basically?
Yeah.
Yeah. So
Would that make a difference?
So I think in the end it won't make a difference, but if it's helpful for you to do the problem, then go for it. You know, the algorithm I give you, you should try to follow as much as you can. But if you notice little things like that, that'll just be helpful for you. I would say go ahead and do it because it won't. As long as you're doing everything correctly, it won't change your answer or anything. But so I guess my answer is you don't have to do that, but if you want to do that, go ahead. I don't know. Did I answer your question? Was it?
Yeah, I'm just wondering if it would change anything or if I had to add anything to it.
I think the only thing it would do is that instead of getting that row of zeros in the bottom, you would end up getting it maybe in the second row or something. It would just kind of move the rows around.
Thank you.
Yeah, no problem. Does anyone else have a question? Okay. Well, if you have a question that comes up, please chime in. I'm going to go ahead and basically summarize now just these possibilities and sort of how to deal with them just real quickly. And then we'll probably switch gears to activities or something. So in summary, what are our possibilities? There's either going to be no solution. I drew a table kind of like this not last time, but back when we talked about systems of equations. There's going to be exactly one, or there's going to be infinitely many. And there's no other possibility. It has to be one of these three possibilities when you solve a system of equations. Either none, exactly one, or infinitely many solutions. And so in terms of matrices, how would you identify these? Well, basically, your matrix, if there's no solution, you're going to get something like this. As you go down and try to reduce your matrix, you'll end up getting a row that looks like this. And then something that's not 0. So I don't know, 5 or something. The point is that for no solution, you'll get a row that looks like this, where there's a bunch of zeros to the left of the bar, everything is 0 to the left of the bar, and then there's something that's not 0 to the right of it. That tells you right away that there's no solutions, as long as you did all your work correctly, of course. So that's your sign that there's no solution. How do I know there's exactly one solution? By this way. So the matrix will look kind of like this. Or maybe I should put it this way. To be really specific, there will be no arbitrary parameters. And no contradictions like we have in this first case also. So there's exactly one solution if there are no arbitrary parameters, and I didn't have like a contradiction or something. And maybe this already covers this, but I'll just be really careful and say that. So no arbitrary parameters, meaning there's a leading one in every column, and there's no contradiction at all. So I don't have any weird rows like this popping up. So I think that should cover exactly one solution. So a lot of the times, maybe it'll look like you'll have ones going down diagonally and then zeros everywhere else. You might have to be careful. There could be extra rows of zeros down below or something, but anyway, who knows what over here. So just keep this in mind. That's exactly one solution. And then for infinitely many solutions, there's at least one arbitrary parameter. Which again means that at least one column is missing a leading one. That tells you automatically that there is infinitely many solutions. And in this case, you should tell me, in this case, you should find that general solution, if you will. So solve it out so that all the arbitrary parameters are on one side of the equations and the non-arbitrary parameters are on the other side, so that you solve the equations for the non-arbitraries in terms of the arbitraries. And so you guys will get a little more practice with this stuff on some activities and whatnot, and of course on the web work as well. Okay, but here's our summary of the situations in matrix format. Does anyone have any questions now? I think maybe that's all I'm going to say today. Okay. I'll point out too, so on Canvas, I've been uploading a few PDFs. I call them helpful guides or something. So if you go on the Canvas homepage and scroll down, you should see something about helpful guides. I uploaded one earlier today about solving matrices, reducing matrices. So, if you want to see written examples that I've worked out, you should take a look at that. I kind of go through step by step. And I'll probably upload another one where there are some of these examples with infinitely many and no solutions, so you can kind of get more feel for what those are like. I think especially this one maybe is trickier for people, so I'll probably upload another PDF of some of these in there, just as a written guide for you to maybe help you out when you're doing your own, because you can never work through enough of these problems. So be on the lookout for that. That'll probably get uploaded later this afternoon. Okay. So that's all I'm going to say today, I think. I think for the rest of class time, you guys are free to work on the activities. I'll kind of leave it up to you. There's 2 activities up. You can kind of work on whichever you want, I think. And of course, I'm going to put you guys into your groups still. And Demetrios and I will be here to answer questions. Just a reminder that I still want you guys to work in your groups. You're very much encouraged to do that, but I do need people to, I think, submit their own activities for now, just because some people, attendance has been inconsistent, sort of, at least for certain students. So I just want to make sure that everyone is having their work accounted for fairly as much as possible. So I'll have everyone turn in their own activity, but please do work together, and we'll spend the rest of class time today working on activities. So I'm going to go ahead and put you guys into your breakout rooms. So sit tight for just one moment.